In calculus, the product rule is a formula used to find the derivatives of products of two or more functions. It may be stated as or in the Leibniz notation. In differentials notation, this can be written as: in Leibniz notation, the derivative of the product of three functions is discovery. Discovery of this rule is credited to Gottfried Leibniz, who demonstrated it using differentials. Argues that it is due to Isaac Barrow. Here is Leibniz's argument. Let u and v be two differentiable functions of x. Then the differential of uv is, since the term du dv is negligible. Leibniz concluded that, and this is indeed the differential form of the product rule, if we divide through by the differential dx, we obtain, which can also be written in Lagrange's notation as examples. Suppose we want to differentiate f equals x2 sin. By using the product rule, one gets the derivative f equals 2x sin plus x2 cos is cos. One special case of the product rule is the constant multiple rule, which states, if c is a real number and f is a differentiable function, then cf is also differentiable, and its derivative is equals c times f. This follows from the product rule, since the derivative of any constant is 0. This, combined with the sum rule for derivatives, shows that differentiation is linear. The rule for integration by parts is derived from the product rule, as is the quotient rule. Proofs. Proof by factoring: let h equals fg, and suppose that f and g are each differentiable at x. We want to prove that h is differentiable at x and that its derivative h is given by f g plus fg. To do this is added to the numerator to permit its factoring, and then properties of limits are used. Rigorous proof. A rigorous proof of the product rule can be given using the definition of the derivative as a limit, and the basic properties of limits. Let h equals fg, and suppose that f and g are each differentiable at x0. We want to prove that h is differentiable at x0 and that its derivative h is given by f g plus fg. Let delta h equals h. Note that although x0 is fixed, delta h depends on the value of delta x, which is thought of as being small. The function h is differentiable at x0 if the limit exists. When it does, h is defined to be the value of the limit. As with delta h, let delta f equals f, and delta g equals g, which, like delta h, also depends on delta x. Then f equals f plus delta f and g equals g plus delta g. It follows that h equals fg equals plus delta f plus delta g. Applying the distributive law, we see that while it is not necessary for the proof, it can be helpful to understand this product geometrically as the area of the rectangle in this diagram. To get the value of delta h, subtract h equals fg from equation. This removes the area of the white rectangle, leaving three rectangles. To find h, we need to find the limit as delta x goes to 0 of the first two terms of the right-hand side of this equation correspond to the areas of the blue rectangles. The third corresponds to the area of the gray rectangle. Using the basic properties of limits and the definition of the derivative, we can tackle this term by term. First, similarly, the third term, corresponding to the small gray rectangle, winds up being negligible because delta f delta g vanishes to second order. Rigorously, we have shown that the limit of each of the three terms on the right-hand side of equation exists, hence exists and is equal to the sum of the three limits. Thus, the product h is differentiable at x0 and its derivative is given by as was to be shown. Brief proof. By definition, if a differentiable at, then we can write such that, also written, then, taking the limit for small gives the result. Logarithms and quarter squares. Let f equals uv and suppose u and v are positive functions of x. Then differentiating both sides, and so, multiplying the left side by f, and the right side by uv, the proof appears in. Note that since u, v need to be continuous, the assumption on positivity does not diminish the generality. This proof relies on the chain rule and on the properties of the natural logarithm function, both of which are deeper than the product rule. From one point of view, that is a disadvantage of this proof. On the other hand, the simplicity of the algebra in this proof perhaps makes it easier to understand than a proof using the definition of differentiation directly. There is an analogous but arguably even easier proof, using quarter-square multiplication, which similarly relies on the chain rule and on the properties of the quarter-square function, differentiating both sides. This does not present issues of whether the values are positive or negative, and the function's properties are much simpler to demonstrate. Note also, these proofs are only valid for numbers or similar, whereas proofs from first principles are also valid for matrices and such like. Chain rule. The product rule can be considered a special case of the chain rule for several variables. Non-standard analysis. Let u and v be continuous functions in X, and let dx, do and dv be infinitesimals within the framework of non-standard analysis, specifically the hyperreal numbers. Using street to denote the standard part function that associates to a finite hyperreal number the real infinitely close to it. This was essentially Leibniz's proof exploiting the transcendental law of homogeneity. Smooth infinitesimal analysis in the context of Lava's approach to infinitesimals. Let dx be a nil-square infinitesimal. Then do equals u dx and dv equals v dx, so that since generalizations are products of more than two factors, the product rule can be generalized to products of more than two factors. For example, for three factors we have, for a collection of functions, we have higher derivatives. It can also be generalized to the Leibniz rule for the nth derivative of a product of two factors. See also binomial coefficient and the formally quite similar binomial theorem. See also general Leibniz rule. Furthermore, for the nth derivative of an arbitrary number of factors, higher partial derivatives. For partial derivatives, we have where the index s runs through the whole list of two n subsets of 1, n. For example, when n equals 3, then Banach space. Suppose x, y, and z are Banach spaces and b. X times y z is a continuous bilinear operator. Then b is differentiable, and its derivative at the point in x times y is the linear map db. X times yz given by derivations in abstract algebra. In abstract algebra, the product rule is used to define what is called a derivation, not vice versa. Vector functions. The product rule extends to scalar multiplication, dot products, and cross products of vector functions. For scalar multiplication, for dot products, for cross products. Note: cross products are not commutative, i.e., instead products are anti-commutative, so it can be written as scalar fields. For scalar fields, the concept of gradient is the analog of the derivative. Applications. Among the applications of the product rule is a proof that when n is a positive integer, the proof is by mathematical induction on the exponent n. If n equals 0, then xn is constant and n xn minus 1 equals 0. The rule holds in that case because the derivative of a constant function is 0. If the rule holds for any particular exponent n, then for the next value, n plus 1, we have therefore if the proposition is true of n, it is true also of n plus 1, and therefore all integral n. Definition of tangent space. Product rule is also used in definition of abstract tangent space of some abstract geometric figure. This definition we can use if we cannot or wish to not use surrounding ambient space where our chosen geometric figure lives. It uses the fact that it is possible to define derivatives of real-valued functions on that geometric figure at a point P solely with the product rule, and that the set of all such derivations in fact forms a vector space that is the desired tangent space.